Hello everyone, I'm Poonam Sharma, your science teacher. Welcome you another session of metals and non-metals chapter. So children, in previous class I have discussed these topics with you, like occurrence or and extraction of metals, how these metals exist in nature, and in which oxide form they will get these metals. So there are certain oxide like oxide ores, sulfide ores, carbonate ores, halide ores, sulfate ores. So these are different oxides, and these different metals are associated with them, and there are different ores from which we are profitably extract metals, and their formulas as well. Now, in a reactivity series, we place metals in a sequence wise. The topmost position attained by the metal is the highly reactive metal, which is sodium and potassium. And the bottom place, which is attained by metals in the reactivity series, are the least reactive one, like gold and silver. So according to their reactivity series, we'll extract metals from their ores by the different methods. And first of all, if we look at the extraction of metals, these extraction of metals can be categorized on the basis of their reactivity: most reactive, medium reactive, and the least reactive one. There are the different major steps or three main steps involved in the extraction: concentration or enrichment of ores, conversion of concentrated ore into crude metal, and third one is refining of impure or crude metal. And so this is the flow chart which I have already explained to you in previous class. And first step I have already elaborated, in which I have taken concentration of ores. How the concentration of ore takes place, in which we remove impurities, or we call it gangue. The impurities which are present with the ores, first we need to remove those impurities, and the process involved in this is known as concentration of ore. So if these metals exist in nature in different oxide form, so according to those oxides, we'll use different techniques for the removal of gangue particles or impurities from the ore. First is hydraulic washing, which is also known as gravity separation, which depends on the difference in the gravity of ore and the gangue particles. Second is the froth flotation, in which we concentrated those ores which are exist in nature in the sulfide form. And the third one is the magnetic separation, in which magnetic substances are separated or segregated from the impure substances, non-magnetic one, with the help of this magnetic separation, in which we use this roller. And third one, the chemical separation, in which we use this method leaching. And generally, like I have taken example of aluminium, which exists in nature in the oxide form, which is known as bauxite. So we remove or we extract pure aluminium from this oxide by the process of leaching, when it reacts with sodium hydroxide, because this aluminum oxide is amphoteric in nature, which acts like both acid and base. So due to this property, we can easily extract it by this process of leaching. So these processes I have already explained to you. And second step is conversion of concentrated ore into crude metal. So if we are taking or converting the concentrated ore into crude metal, so there are different processes involved into it, and these two main methods are roasting and calcination. As I told you, in roasting sulfide ores are used, and in calcination carbonate ores are used. So these are the differences between roasting and calcination. So we have done, I think you have revised whatever I have taught you in previous class. And children, this table is extremely important. Generally this question comes in 2 marks: differentiate between roasting and calcination. So if this question comes in the exam, so you'll write all these points of differences between roasting and calcination. So how this roasting takes place and how this calcination process takes place. Now second is the next method is reduction. So if we heat those oxides of metals, then turn into metal is known as reduction. So it means we are reducing. When we are heating their oxide ores, We have converted metals into their oxide form because it is easy to extract metal from their oxide form. So if once we get oxide form of the metal, so we can reduce it into pure metal, and this method is known as reduction. First is extraction of metals of least reactivity. As I told you in reactivity series, some metals are placed at the bottom. So they are least reactive metals. So these least reactive metals, they can be extracted from their ores which exist in nature by this method. And how they are extracted, let's look at the example. Because they are unreactive metals, so they'll burn in air. And if they'll burn in air, so they'll produce some oxide, and then it is easy to obtain the pure metal from their oxide form. And if we'll heat them alone, then only they'll convert into oxide form. Let's see first example of mercury metal. Mercury is extracted from its ore, which is cinnabar, and its formula is HgS. So this is the ore of mercury. Ore of mercury, from which we can easily extract it mercury. So this ore is heated in presence of air. When it is heated in presence of air, it converts into mercury oxide and it releases sulfur dioxide gas. As I told you, it is easy for us to extract metal from their oxide form. So first we'll convert these ores into their oxide form. So as you can see here, when this cinnabar is heated in presence of oxygen, it results in the formation of mercury oxide. And then this mercury oxide is heated strongly alone, and which reduces into mercury and oxygen gases evolve. So this is how we extract mercury, which is considered to be less reactive metal, because they'll not react with any other substance. Another example of such kind of metal is copper metal. So with the help of this reduction process, we'll extract copper. So first of all, we'll take ore of copper which exists in nature in copper glands. And the formula of this copper glands is Cu2S. So when again it is heated in the presence of air. Here you can see S. It means it is present in the sulfide ore. And for sulfide, we do roasting. So here roasting process takes place. So when this copper glands heat in presence of oxygen, it results in the formation of copper oxide and sulfur dioxide gas is released. Now this copper oxide is heated in the absence of air, which results in the reduction of copper and sulfur dioxide. Now these are the steps. Cu2S. So this is heated in the absence of air. So this results in the formation of copper oxide. Then we have extraction of metals of middle reactivity. Middle reactivity means these metals are placed in the middle of the reactivity series. And examples of such kind of metals are iron, zinc, lead. So they are found in the form of carbonates and sulfide ores. And if you remember, we use carbonate and sulfide ores. So which method we use for these ores? Write in the comment box. This I have told you earlier. For carbonate or sulfide ores, we use certain particular method. And what do we call that method? So first of all, these carbonate or sulfide ores are converted in their oxide form, and then from these oxides metal can be extracted. So look at the examples of such kind of metals. First is zinc. Zinc exists in nature in the form of zinc blende, or we call it zinc sulfide. For sulfide we do roasting, and if it exists in carbonate form we do calcination. So let's see, both the examples are in front of you. When zinc blende, or we call it smithsonite or zinc spar or calamine, are the ores of zinc. So these are different ores. If you remember, I shared one table with you in which metals and their ores are present. So zinc can be exist in nature with sulfide ore, with carbonate ore, and this is known as the different ores of the zinc. So zinc blend, if you are talking about zinc blend, because it contains sulfide. So if we convert this zinc blend, it is the roasting process takes place, because here it is associated with sulfide ore. So here, due to the process of roasting, this zinc blend is heated in the presence of oxygen, which results in the formation of zinc oxide, and sulfur dioxide gases evolve. And if we are talking about zinc carbonate, in which very less supply of the oxygen is there, it convert into zinc oxide, and then carbon dioxide gases evolve. So these are the two processes which takes place in the extraction of zinc with the help of roasting and calcination process. So zinc oxide, which is formed, it is reduced to zinc metal by heating with carbon. So when we get this zinc oxide, we heat this carbon, which act like a reducing agent, because it reduces and combines itself with oxygen. Then it results in the formation of carbon monoxide gas, and zinc is left behind. So as you can see, we'll get the pure form of zinc. So this is how we extract the zinc from its ore which exists in nature. And this zinc exists in nature in the sulfide form and the carbonate form. For sulfide, we do roasting, and for carbonate, we do calcination. So by using those two processes, we are extracting zinc from their ores. The next is extraction of iron from hematite. Hematite is a name of the ore of iron. It's a 1-mark question. Name the ore of iron. And the answer is hematite, and formula is Fe2O3. So hematite ore is first heated. As I told you, these ores are heated and with carbon. Now this, when heated with carbon, so this carbon combines with this oxygen, which results in the release of carbon dioxide gas, and as a result we'll get iron. So this is how we'll extract iron from hematite ore, which is Fe2O3, when we heat iron oxide in presence of carbon, which results in the formation of iron, and carbon dioxide gases released. So as you can see how these metals are extracted from their ores. Another example of metal which exists in the middle of the reactivity series is lead. So lead is extracted from lead oxide. So when lead is present in nature with oxygen, so this oxide is heated in presence of carbon, which results in the formation of carbon dioxide gas, and we get lead. If you'll see these two here, iron and this lead, they both heated with carbon, and they both results in the release of carbon dioxide gas. If you look at these two metals and their extraction, so they release same product, which is carbon dioxide gas, and will get pure metals. Now reduction of metal oxide by heating with aluminium. So there are certain metal oxides which there are certain metals rather we can say, which exist in nature with their oxide, because as we know oxygen is a very reactive one, so it can easily react with the metals. So when these oxygen react with metals, it forms metal oxide, which we have done when we were doing chemical properties of metals. And if you remember, any metal when react with oxygen, it results in the formation of metal oxide. So if these metal oxides are present in nature and we want to extract metal from their oxides, so that's why we are doing this reduction process. Here we are reducing metal from their oxides. Now another example is aluminium. When we are heating metal oxides with aluminium, earlier we heated metal oxides with carbon, now we are heating with aluminium. Let's look at the example. So when we heat metal oxide, an example of such kind is manganese dioxide. So if manganese reacts with oxygen, it results in the formation of manganese dioxide. So when we heat it with aluminium, it results in the formation of manganese, and aluminium oxide is released. And when this copper oxide, again copper exists in nature with different in different forms. It exists in nature with different ores. So here, if copper oxide is there, if copper exists in nature in its oxide ore form, so in that form we heat copper oxide with aluminium, which results in the formation of again aluminium oxide, plus heat is released and we'll get copper. As you can see the difference, when the metal oxides heated with carbon, they result in the formation of carbon dioxide gas, and if metal oxides are reduced or heated with aluminium, it results in the formation of aluminium oxide. So in this manner, we'll reduce the metals or we'll get the metals from their oxide form. Then one reaction is thermite reaction. It is very important reaction, as the name itself says, thermite. It means some heat is involved into it, or it is related to some temperature. So it means an example of such kind of thermite reaction is when this iron oxide, or we call it ferric oxide, is heated in with aluminium. So when we are heating iron oxide, it means here iron when combined with oxygen, this is the oxide form of iron. It means this is the oxide ore of iron. When it is heated with aluminium, it results in the formation of aluminium and aluminium oxide, and iron is released. Plus it releases tremendous amount of heat. Now, and this kind of reaction is used in the welding of electric conductors, iron joint, because it releases tremendous amount of the heat, and in joints in the railway tracks. And this is also known as thermite welding. It means with the help of heat, we are joining the joints. It means when heat is released, that heat is responsible for joining the joints, and that's why we call it thermite welding or TW. So this is thermite reaction, in which ferric oxide is heated with aluminium, which results in the formation of iron and aluminium oxide, plus it results in the release of tremendous amount of the heat. Now, what kind of question can come in exam on the basis of these topics? The question can become how extraction of metals takes place. Suppose they'll ask how zinc can be extracted from zinc blende. Then in that case, you need to write this equation only. If zinc sulfide reacts with oxygen, it results in the formation of zinc oxide and sulfur dioxide gas is released. Or question can come, explain extraction of zinc from its zinc carbonate. So then you have to write this equation. Or question can come, which process we use for the extraction of zinc from its zinc carbonate. So you'll write calcination process. And the process which is involved in the extraction of zinc from zinc blende is known as roasting. Or which gas is released when zinc oxide reacts with carbon? And the answer is carbon monoxide gas. A question can come on iron. Name the ore of iron, and the answer is hematite. Or question can come, which gas is released when iron oxide is treated with carbon or heated with carbon? And the answer is carbon dioxide gas. Or question can come in exam, describe the extraction of iron from hematite or from its ore. So in this question, you need to write entire equation along with its explanation, which is written here. A question can be based on extraction of lead from lead oxide. Then in this question, you need to write the equation which takes place between lead oxide and carbon, which results in the formation of or extraction of lead and carbon dioxide gases released. So question can come in any ways, either on the extraction of these metals or what kind of products are released when their oxides are combined with these different substances. And one more example, like one more question is here, like how we can reduce or what will happen if manganese dioxide reacts with aluminium, or how can we reduce manganese from manganese dioxide. So in both the questions you need to write this equation, only this one. And if the question comes, how can we get copper from copper oxide ore, then in that question, you'll write this equation. So when copper oxide treated with aluminium, it results in the formation of copper, aluminium oxide, and heat is released. And very important question, describe thermite reaction. It's a 2-mark question. Or what is thermite welding? So in this, you need to write this explanation plus give this reaction. Or question can come in 1 mark, name the reaction which is involved when the iron oxide treated with aluminium, and the answer is thermite reaction. So these kind of questions can come in exam on the basis of these different extractions. Now there are certain metals which are placed at the top of the reactivity series. Being highly reactive in nature, they can easily react with any other substance if we extract them or if we treat them with any other substance, metal or non-metal. Like in case of these, we have reduced these metal oxides with aluminium and carbon, which I have explained. But if we are talking about metals which are highly reactive in nature, so they are extracted from their ores by electrolytic reduction. There is one process which is known as electrolytic reduction. It means we are reducing metals from their ores by passing electricity. So with the help of this electricity, we are getting metals from their ores. And these metals cannot be reduced using carbon, because carbon is less reactive than them. Because only, as I told you, less reactive cannot displace the more reactive one. Here, aluminium and carbon, they are more reactive than the given these oxides, so they can easily displace it. But if we are talking about highly reactive metals, we cannot use carbon and aluminium because these metals are so reactive, so though other metals cannot displace them. So that's why we need certain unique technique for their extraction, which is electrolytic reduction. Now, what is this electrolytic reduction? How it takes place and how we'll extract metal from this electrolytic reduction? Just look at the example. As I told you, when electricity is passed through the molten state of a metal ores. Molten state means if it is present in the liquid form of the metal ores. So then in this form, we easily get metal, and metals, as we know, they are electropositive in nature. They contain positive charge, so that's why they deposit over the cathode. And when electric current is passed through the molten state, so this positive charge metals are moved towards the cathode. For example, if we look at the example of this electrolytic reduction, as you can see here, NaCl. NaCl is the common salt or the sodium chloride. This is sodium chloride, which exists in nature in NaCl. So when electricity is passed to the molten state, then what will happen? At cathode, this reaction will take place. So here sodium loses its electron and moves towards the cathode, which results in the formation of sodium metal. And at anode, chlorine moves towards the anode, which results in the formation of chlorine. So when this sodium chloride dissociates on passing electricity through it, it results in the formation of sodium and chlorine. So here, this takes place at cathode and this takes place at anode. So these move towards the positive electrodes, and there are two electrodes. Like this is a beaker in which two electrodes are present, which are connected with the battery. Here it is cathode and here it is anode. And cathode is negative and anode is positive. So sodium, because it contains positive charge, that's why it moves this is, I'll write cathode, I'll draw again. These are the two electrodes which are present here, cathode, anode, and if we pass electricity through this molten state of NaCl, and when we connect it with the battery, then this Na move towards the cathode and Cl move towards the anode. So these are the reaction which takes place at cathode and at anode. And in this manner, we'll get sodium and chlorine. So I hope till here it is clear to you. Or one more example I'll take for this electrolytic reduction of aluminium oxide. Now look at the example of aluminium oxide. I'll write this equation here. When aluminium, which has 3 electrons, so it means it is losing 3 electrons and it becomes aluminium metal, and this reaction takes place at cathode, and the reaction which takes place at anode is 2O2 minus, it is losing 2 electrons and it becomes O2. And the overall reaction is Al2O3 on electrolysis will get plus 3O2. Electrolysis means when we are passing electricity through it. So it results in the formation of aluminium. So this is one more example of electrolytic reduction. It means when we are passing electricity, it results in the formation of aluminium. So we'll extract aluminium from aluminium oxide on passing electricity through it. So this is how electrolytic reduction takes place. Now, next is refining or purification of metals. The refining or purification of metals mean metals extracted, as we know we are extracting metals from different methods which contain certain impurities. Now still these metals contain some impurities along with them, so we need purest form of the metal, and those metals can be refined or can go through a process which we call electrolytic refining. So it means due to the electrolytic refining, we'll get the purest form of metal. And how this refining takes place. Now look at this example. In electrolytic refining, so we'll take impure metal and a thin strip of pure metal dipped in the salt solution of metal to be refined. So how it will take place, I'll explain it with the help of the example. So when we pass electricity through it, through that solution, pure metal deposit on the one stripe, and then impure metal is used as an anode and pure metal is used as cathode. Now let's see how this electrolytic refining takes place in particular metals. Example of such kind is copper. As you can see here in this diagram, cathode and anode is here. And here we have taken copper metal. Now this lump of impure copper metal and thin strip of pure copper are dipped in the solution of copper sulfate. It means here this molten state is copper sulfate. As I told you, we'll extract copper from its molten state. So here molten state is copper sulfate solution. Now what will happen in this case if we'll pass current through it? When we are passing current, the pure metal from the anode start moving towards the cathode, and as a result there is a decrease in the size of anode, because this metal which we are using as anode, it has certain impurities into it, and then it starts dissolving in its molten state and copper start moving towards cathode, because this copper contains positive charge and cathode is negatively charged. So positive start moving towards the negative. So this anode first dissolves into this molten state or this solution, and from here copper starts depositing on the cathode. So when this process is taking place, there is a decrease in the size of anode and increase in the size of cathode, because as you can see, it keeps on dissolving into molten state in this solution, and this copper start depositing on it cathode, and this reaction takes place until the entire anode is reduced and it deposit on the cathode and the size of cathode becomes heavy. So once all the anode get dissolved into it, then we stop the reaction, and the impurities which are dissolved into this salt solution, it get deposited as anode mud. So those impurities which are left behind, they'll dissolve in this solution and it deposit here at the bottom near the anode, and we call it anode mud. So anode mud is the impurity. Okay, so this anode mud is the impurity which accumulate near the anode as an anode mud, and the pure one, pure copper, deposit at the cathode. And then when entire cathode, this copper deposit on the cathode, we stop the reaction, we take out the electrodes, and we'll take out the entire copper pure metal from the cathode. And the reaction which takes place at anode and cathode is somewhat like this. So at anode, this reaction takes place, and at cathode, this reaction takes place. So here copper is reduced to copper ion, and at cathode copper is accepting electrons from the salt solution and will get pure form of copper. So this is how electrolytic refining of copper takes place. Children, it's a very important question. It's 3-mark question. So you need to explain the entire method of electrolytic refining of copper. So when this question comes in exam, you have to explain the entire process in detail and what kind of reaction takes place at anode and cathode. And you need to draw this diagram also. So with the help of diagram, you can explain how this electrolytic refining of copper takes place. So this is electrolytic refining. Now next is corrosion. See, most of the metals, if they comes in contact with the air, they'll reduce in size. They form one layer over it, which results in the corrosion. And this is, as a result of this corrosion, there is a wastage of the metal takes place. And this method is known as corrosion, when metals comes in contact with the oxygen. Now first is rusting of iron. And this is the best example of the corrosion. When iron comes in contact with oxygen, so it reduces in size, it forms iron oxide layer, which reduces the iron, or there is a wastage of iron. And we need to prevent that rusting, because every year there is a heavy loss of iron, because iron being heavy metal we use in the construction of buildings, railway tracks and in bridges. So if we use iron for making them, so we need to protect them. It needs lots of maintenance. Lots of money is spent every year on the maintenance of these bridges, these buildings and these railway tracks. Then how can we prevent rusting? There are certain methods with the help of which we can prevent rusting, or we can protect the iron from coming in contact with oxygen and water. So these methods are painting, greasing, galvanization, electroplating and alloy. If we paint iron object, we can protect it with that iron does not come in contact with the oxygen, so because this paint layer acts like a barrier. Same with the greasing. If we do greasing, that greasing always acts like a barrier layer, which does not allow the iron to come in contact with the oxygen. Galvanization is a deposition of zinc over iron. So when we deposit a layer of zinc, and this can be done by passing electricity through it. So with the help of electricity, when we pass current, then zinc can deposit on the iron, and with the help of it, it can easily prevent. Then electroplating, with the help of electricity, we plate or we deposit a layer of one metal over the another metal. Then we have alloying. Alloying is the mixing of two metals together, which enhances the strength and durability of those metals. And alloys are considered to be homogeneous mixture, because once these metals mix together, it is difficult for us to identify their boundaries. And types of alloys are, first is ferrous alloy, in which iron is present, and this is a combination of manganese, steel and nickel steel. This much percentage of these metals and non-metals are present in ferrous alloys. Then we have non-ferrous alloys which do not contain iron. So ferrous alloys are those in which iron is present, and non-ferrous alloys are those in which iron is not present. And examples are brass and bronze. And this amalgam is an alloy in which mercury is present. Example is sodium amalgam and zinc amalgam. So these are different alloys. Ferrous alloys in which iron is present, non-ferrous in which iron is not present, and amalgam in which mercury is present. Now, there are certain properties of these alloys. They make the metal more stronger, and it is harder than the metals which are involved in its making. It is resistant free. Melting point of these alloys is lower than the metals which are involved in its making. An example is soldier, which contains tin and lead, and it has lower melting point than tin and lead. Then electrical conductivity is lower than the metals. So these are the properties of alloys, which are a combination of different metals together. Certain more example, it is very, very important. These are the examples of alloys, like brass, which is a combination of 80% copper and 20% zinc. Bronze, which contains 90% copper and 20% tin. Then soldier, 50% lead and 50% tin. Then duralium, It contains 95% aluminium, 4% copper, 0.5% magnesium and 0.5% manganese. Then we have steel, which contain maximum amount of iron and minimum amount of carbon. Then we have stainless steel, which contains 74% of iron, 18% chromium and 8% nickel. Then we have magnesium, which contains 95% aluminium and merely 5% magnesium. Then we have German silver, which contains 60% copper and 20% zinc and 20% nickel. Okay, now these are the different alloys. Now alloys of gold, because pure gold is quite very it is very weak. So if we make ornaments with pure gold, we can easily bend, it can easily break. So that's why we add some amount of silver or copper to make it hard. So these are the different alloys, which are the combination of different metals. So I hope this chapter is clear to you, and go through all these topics in detail. So in next class, I'll take some important questions from this chapter. So we'll discuss question answers of this chapter according to exam point of view, which considered to be very important. So before that, please go through all the topics in detail. So till then, take care and goodbye.